sklearn Ensemble Hist Gradient Boosting Regressor. Description: Hist Gradient Boosting Regressor is a powerful gradient boosting algorithm designed for regression tasks. It leverages the strengths of histogram-based gradient boosting, enabling it to handle large datasets efficiently while maintaining accuracy. Unlike traditional gradient boosting methods that use individual data points, this algorithm uses histograms to group similar data points, thereby speeding up the training process and reducing memory usage. Inputs: XA2D array representing the input features of the dataset. Each row corresponds to a sample, and each column represents a feature. YA1D array representing the target values corresponding to the input features. Outputs: predictions: A1D array containing the predicted values for new input data. Steps: initialization: the algorithm starts by initializing a constant model that predicts the mean of the target values. Iterative boosting: it then iteratively builds an ensemble of decision trees by computing gradients, calculating the residuals differences between actual and predicted values for the current model, building trees, training a decision tree on the residuals to capture the remaining patterns, updating model, adding the new tree to the ensemble, weighted by its importance. Metrics: mean squared error MSE measures the average squared difference between predicted and actual values. Root mean squared error RMSE the square root of the MSE, providing a more interpretable measure of error in the same units as the target variable. R squared R2 represents the proportion of variance in the target variable explained by the model, ranging from 0 to 1, with higher values indicating better fit. Visualization plots: feature importance plot visualizes the importance of each feature in the model, indicating which features contribute most to the prediction. Partial dependence plots show the relationship between a specific feature and the target variable, holding other features constant. Tree visualization allows for viewing the structure of the individual decision trees in the ensemble, providing insights into the model's decision-making process. Fine-tune parameters: learning rate controls the step size at each iteration. Smaller values result in slower but potentially more stable learning. Maxiter sets the maximum number of boosting iterations. Max depth specifies the maximum depth of the individual decision trees in the ensemble. Limiting model complexity: L2 regularization applies L2 regularization to prevent overfitting. Min samples leave minimum number of samples required to split an internal node, limiting tree growth and preventing overfitting. Uncertainty methods: confidence intervals can be calculated based on the ensemble's predictions to provide an estimate of the model's uncertainty in its predictions. Prediction intervals can be used to provide a range within which the true target value is likely to fall. Challenges and fixes: Challenge 1: overfitting, when the model learns the training data too well and performs poorly on unseen data. Sample use case that resulted in challenge 1: using a high number of boosting iterations Maxiter, or allowing trees to grow too deep. Max depth can lead to overfitting. Fixes to challenge 1: reduce Maxiter, limit the number of boosting iterations to prevent the model from becoming too complex. Decrease max depth, limit the depth of individual decision trees to prevent them from becoming overly specific to the training data. Increase L2 regularization, applying L2 regularization can help prevent overfitting by penalizing large coefficients. Challenge 2: computational cost, training a Hist gradient boosting regressor can be computationally expensive for very large datasets, especially with a high number of features or boosting iterations. Sample use case that resulted in challenge 2 training the model on a dataset with millions of samples and hundreds of features could lead to significant training time. Fixes to challenge 2. Reduce max iter. Limiting the number of boosting iterations can significantly decrease training time. Consider early stopping. Monitor the model's performance on a validation set during training and stop training when performance no longer improves to avoid unnecessary iterations. Utilize feature selection techniques. Identifying and removing irrelevant features can reduce the model's complexity and improve training speed. Optimize hyperparameters. Fine-tuning parameters like learning rate and max depth can impact training time and performance.